speakers because this is about real-time collaboration, as far as I understand, and I guess we'll have some real-life demo.
Yes.
So this is Project Alva, and we're looking forward to your presentation.
Thank you.
Yeah, thank you so much. I'm Jakob, I'm from Berlin. I studied physics and got to know lots of cool stuff. But what hooked me the most was the first course on Python introduction, the first semester. And since then, this interest grew into, you can say passion for open source software and Linux and texturized terminals. And now I find myself maintaining an open source project, Alva, which combines all these nice things together. And Tiziano,
yes. I have two lives. In one, when I'm Dr. Jekyll, I work at the TU Berlin, Technical University in Berlin. I teach programming. And on the side, I also work with Jakob at the Alva project. And when I'm Mr. Hyde, I am a psychotherapist and help people with their problems they get when they work with computers. So, let's start, because we have just 20 minutes.
Yeah.
So I will be taking notes live of the talk. So I'm writing in the meantime the notes. And it happens quite often when you teach or when you have a talk. Well, you would like to share what you're doing with the people in the audience, right? So I just started an hotspot on my machine. And if you want to play along, you can just connect your laptops. With the phone, I think it's not a good idea. You need a terminal. Do you want to show what the SSD is?
Yes. So
so you connect to network
device, whatever.
First. Yeah.
So I'm not connected right now. I want to connect to talk, which needs a password called password in capital letters.
So you can connect right away?
Right. And now my IP is 10.42.0 dot something. And
So in order to share the notes, I start the sharing thing on my laptop. You will see in a second how it looks like. And I start editing the notes in the editor, in my terminal. Right. And then I want Jakob to join. And you can type along if you want, you can join too. And we take notes together. That would be nice.
So you're typing already?
Yes.
Right, then I will start the editor myself. This you will do with the Alva command, Alva editor. Editor is the Alva app we will start. Then we need to specify our host, which is, in our case, on the IP 10.42.0.1, Tiziano's laptop. Then the port is quintuple 1, 5 times 1. And then you need to specify an identifier, which is in our case alva-talk-nodes.
That's it.
Not already, because we are not using SSL context here. We need to also specify an unsafe flag, which is for the time being the only way to connect to a self-hosted server. But let's run this command, which fires up the editor. And now I got already the content from Tiziano. Right, and he's writing in real time now into my editor, and I can see his notes.
So if you want to join, I'll write the notes here. Now you are seeing them. So I don't know how you do it. Create an env for Alva and activate it. I'm not typing here the commands because everyone has a different idea how you create envs. The cool guys do it with UV, I do it manually still. And then when you are in the env, you install Elva. It should just work. And after you have installed Elva, it may take a couple of seconds because there are some dependencies. Right. You just join with this command that you have seen. Unfortunately, the font is so big that it doesn't fit in a line. So let me see if I can make it fit like this. No, I can't.
But it fits on my screen.
It fits in your screen? Oh, perfect.
Yeah, this is all right. So,
you have to be in the talk network, right?
In
the talk network, yes.
Right.
Yes. Well, my laptop has limited capabilities. Don't start downloading your preferred torrent movies right now through the hotspot. We are doing it, by the way, on a hotspot here because the network of the university is blocking communication between clients. Otherwise, we could do it in any network. So, as you see, well, let me check. How do I check the dashboard?
Control B. So with Control V, you can fire up a dashboard, which for now just shows you the current use configuration and the active clients in the room. So currently it's just me and Tiziano, apparently.
But in the meantime, while you are connecting and not messing up with our nodes, apparently, well, persistence use case.
Persistence use case. What we can do now is that I can just close my editor. And now I'm at this, just an empty directory. There's nothing in here, no files, nothing. But when I connect to the same identifier with the same command, I got the content back from Tiziano. So this is synced back, and I can start working again on here. Whoops.
So you don't have a local copy of this anymore?
No. I don't have a local copy. There's nothing on my disk. Right.
So this thing lives in the network at the moment.
Right. What I can also do is I can write or type along while I am offline. And when I reconnect, it gets resynced. So that's how it works. So what I do now, I have I'm still connected. When I disable my Wi-Fi, I'm disconnected. Nothing happens now. Nothing's synced. And I can type here while I am offline. And now let's reconnect to talk. All right, we're back online. And now we wait for the provider component working for the or responsible for the connection to reconnect to Tiziano's server and to resync.
In the meantime, I see that someone joined without a name identifier, so you are anonymous at the moment, my friend. So, may take a while because of TCP exponential timeout, so it will come back. And while it comes back, you can...
So we're back.
You're back. You see that the stuff has been updated.
Did I?
No, you're still not back.
I'm still not back. Right.
Stefan, okay, so you see someone joined.
Now, okay. What did he type? Questions from audience? No.
Yeah, someone asked here if...
How to exit the editor? Yes, it's Control Q.
Yeah, exit or go back? How does it look like?
Go back? What?
Exit the editor and connect again.
Okay, let's reconnect. Ah, okay, now it's synced.
Now we're there. Yes. Well, live demo. So stuff happens or doesn't. But now the right question was, where is the file, right? There's nothing there. Well, we can add persistency. Can you save the file?
I can. So with Ctrl S, I just type in a name, file name, test.chat. No, not just test.text. Right. So now when I am back here in my other terminal, I can see there is some file created. So actually two files, one test.txt and one test.txt.y. The .y file is the main file for the Elva apps, where all updates get saved one after another, and the test.text is the rendered file, what your content actually looks like, what is rendered file. And now when I close my editor, then I can specify this this file, and it will reload and reconnect to the room, because the identifier is stored alongside the updates in the data file. I can also, again, go offline, no IP there, and restart the editor, and now I can also work on content here.
So, but just an editor would be boring, right? So we have
also a chat app.
A chat app.
Right. So what you can do is then basically just changing the identifier from Elva Talk Notes to Elva Talk Chat, and starting the chat app. And now we opened a new room. Let's switch to another site. It's just me in the chat.
What is it called?
Do you mean identifier?
Yeah.
It's Elva Talk Chat.
It's not.
It's not Elva Talk Chat. You specify unsafe.
Yeah. That's that's interesting. Okay. Are you online?
I'm not. This might be the issue. You need to be online, right? Right. Okay. Let's
Start the chat.
Let's show this chat. Make it a bit bigger so I can read along. Tab. Talk. And then we do an Elva chat. And there we go. Hey Stefan. Nice to see you.
And note that you can write Markdown. So we don't have enough a lot of time. So these are just two examples, but now a bit of background.
Yeah, right. So Elva uses internally conflict-free replicating data types, or short CRDTs, to realize these real-time updates. So actually, you have your basic data types like text or an array or a map, and these data types gets integrated into a Y document, you would say, and every change to those data types is translated into an update, which you can send over some connection. This is not limited to internet or Wi-Fi. You can also use Bluetooth or other types of connections. You just need to transfer the update from one endpoint to another. And the original implementation of those YCRDTs has been done by the YJS library. Maybe you heard of this before, which is one of the biggest names for in-browser real-time editors. And if you want to use those YCRDTs within Python, there's the PyCRDT bindings repo in the YCRDT GitHub organization. Right. And in the end, we have Elva as an end-user interface and framework, which also delivers some built-in modules like the app you've seen in the chat. And the app itself is only about 200 lines of code long, so you can basically write one yourself with little effort. And the chat is about 400 lines of code, so a bit more advanced, but also not very big. And you're not limited to those text editors or chat apps. You can basically write any app you want. The server is also an app in the from the Elva framework. You can also make a file sync app, which watches your file directory and syncs files and content if you like, or many other things you can think of. Yeah, and you can write your own app if you like to. You just need to specify your app as a namespace package, which is described on the in the Elva docs. So yeah, and as yeah, and bottom line is that you have a local first app or framework for writing apps, which also delivers conflict-free collaboration and with optional persistency. So you're not bound to having files, but you can.
Come on, Jakob, this is boring. I mean, there is Google Docs, Google Drive, iCloud. There is all of this stuff already. So why would you start doing something like that? I don't get it. Dropbox?
Yeah, because not open source. You need an account, privacy issues, stuff like this. So, but maybe Nextcloud could be.
Well, but Nextcloud, okay, it's open source. On the other hand, have you ever tried to install Nextcloud? You need to manage a server. You need an admin if you want to do this. You need network. And you still have merge conflicts all the time. Like if you edit a file on Nextcloud, I edit the same file, and because we share that file, this is going to conflict. You will get this threaded error in the Nextcloud sync app. So Nextcloud, it's not good for this. So, but maybe Etherpad, EdgeDoc, maybe you know this thing. So, to collaborating online note taking.
No, but an Etherpad, it's only in the browser, and you can't save files if you like. But you need to download them manually by hand, which is cumbersome. But maybe Git.
Well, okay. I mean, in principle, Git does all of what we are seeing. So history, you can several people collaborating, but of course Git has a different use case, right? So if you would write an editor based on Git for collaboration, then when do you commit? What do you commit? And Git also refuses to take over the job of merging the conflicts. So when there is a merge conflict, Git complains. CRDTs, the protocol, is written in a way that it has a kind of an optimistic view on merge conflicts. You just smash everything together and hope that people will fix it. You have seen it now in our writing together that all the lines, they appear at some point. So it may be a bit dangerous, but as you've seen, I'm giving a talk. I just started right away. No installation needed, no server, no admin, and then we can work together. So.
Right.
80 minutes where we didn't convince you probably, but come and talk to us. We can talk about the details, and it is actually a nice idea. Well, thank you.
Thank you very much.
And,
I mean, we already started the discussion
yes,
between you,
exactly.
and we can continue. We have time for a couple of questions.
Yeah, so I really love the idea, but I'm confused with it's a conflict-free, but that it's just because you mash everything together. But it seems to me like you're stomping over the conflict. I don't know if you're solving it anyhow. I mean, can you elaborate on this?
Well,
How does it solve the conflicts itself?
yeah, so the optimistic approach basically turns out to be quite useful because you're merging little updates. You're basically updating every single character, which you wouldn't do in Git. And that's why you can be optimistic on those merges, because the impact on not desired merges is not that big actually. So what we expected in merging those divergent histories when I wanted to reconnect was that the lines get appended after each other. So this is not desired, maybe, but also not that bad.
But you can fix it in a protocol, no? Like you decide what an update is. In an editor, you would update every single character. Imagine you are now editing XML, like you are writing now a LibreOffice real-time collaboration plugin. Then, because it is XML, an update would be XML, how do you call it? A tag, open and close. And this is going to be a full update. So you ensure consistency in the protocol defining what an update is. You still with this idea that if I, let's say, select some characters and say bold, it would select the same characters and say italics. Then at the end, when the update happens and the sync happens, we will have it twice. Once with the bold, one with the italics. But basically, you don't lose information. In the worst case, you have too much.
Time for one short question.
Is it currently possible to hook up your own editor and to collaboratively, securely edit a document, like over the internet, or is that stuff that has to be built?
So the framework allows for it already. We will need to do the work of writing the Vim or the Emacs plugin for it. But there's nothing. It's in principle it's the same. It's like a Git plugin. So it is. Is this me? It's me. But no, we didn't write it. But the framework allows for it already. So it would be a matter of writing the code. I would expect 500 lines of code.
Probably.
Okay, so I think we ran out of time. Thank you very much for this impressive live demonstration.
Thank you.
Let's thank Taco for
We have to go on because there's the next talk. Mm-hmm. You have to switch it on. No.
No, I just have to bring it back to the room that I borrowed because they're gonna have a talk.
I think in principle this should work, but I'm not sure.
Okay, we'll see.
Try the first one.
Should I do something or is it running already?
I'm not sure about it. This local guy, he probably.
Hi.
I'm not sure whether he checked it. He said he would check it, but
I think it's not turned on.
we decided that the cable is going somewhere. But so I'll give you a sign after 15 minutes. Then you still have 5 minutes. It's 15 plus. So after 10 minutes, so that will be 2/3, and then 2 minutes. And
Okay.
we are a bit flexible.
Okay,
If you take longer, there will be fewer questions in the end.
Okay, I think I could fit in this 15 minutes. I was sure that it's 20 minutes for talk only, but if I hurry up, 15 minutes would be enough, I
There is some
think.
flexibility, so don't worry too much. But I'll just give you a sign. And
Okay. I have some issues. It's not booting. So.
Oh, okay. That's
Oh. A co, problem jest na razie po prostu z komputerem.
Tak.
Okej.
No, nie spodziewałem się tego. Przed chwilą się butował normalnie.
Masz jakiś backup tego?
No mam te prezentacje, tak.
No to na tym można puścić bez problemu.
No, tak.
Tylko, że jak miałeś jakieś demo, nie? Albo coś.
Nie, tylko mam prezentację. Więc powinno być ok.
just put it on the...
Yeah, we are going to do that. Tylko się muszę na maila swojego dostać.
Dobrze, dobrze.
To nie ma problemu. Tu mam.
To okej, to ja już w międzyczasie to podepnę, żebyśmy to mieli.
Ja sobie tylko tutaj na telefonie skrypt odpalę.
Tak, to jest...
Dobra, super. To zaraz się zaloguję na maila bez tego. Jaka tu jest przeglądarka?
Hasło... Tak, nazwa jest...
To nie wiem, jakbyś mógł to zrobić. Ja sobie u siebie na telefonie tylko skrypt odpalę.
Dobra, możesz...
Dobra, ja tu tylko sobie notatki odpalę. No tylko tu podobno mikrofon jeszcze jest i...
Znaczy, on jest bardziej do zbierania z sali,
Aha.
więc będziesz
Trzeba
pisał,
mówić.
czy...
Będę mówił, tak.
To mówisz to najlepiej do tego, chyba że wolisz ten krawatowy, te są bardziej niezawodne.
To wolę bardziej niezawodny jednak.
No to masz ten. Czekaj, bo teraz go włączyłem czy wyłączyłem? Włączyłem.
Okej.
Dobra, to mogę wpinać?
Tak. Tylko zaraz jeszcze... O Boże, jak to się... Dobra, już.
Dobra. Jest i jeszcze jedna rzecz. To jest to do zmieniania slajdów i pointer. Tu masz pointer, tu zmieniasz dwie strony slajdów.
Dobra,
Spokojnie, jesteśmy o czasie.
okej.
Okay, I think we should get started again. Our next speaker is Adam Staniszewski from the local university, from AGH. And he will tell us about distance calculations in large molecules, which is an important problem in biology and chemistry of large molecules.
In chemistry mostly, yes.
Yeah.
So
you can explain the details.
So as I was introduced, my name is Adam Staniszewski. I'm a graduate student at AGH at Krakow, and I do research at machine learning and chemoinformatics lab, which operates at this very faculty. And I prepared a talk on distance calculations in chemoinformatics. So for starters, what is chemoinformatics? It is an interdisciplinary field that uses computational techniques known from computer science to solve problems related to chemistry in some ways. So trivially, the problem might be administrating database of molecules, but more ambitious one, I would say, involve representing molecules, measuring similarity, quasar modeling, which is regression and classification on chemical data, and virtual screening, which is probably the most relevant for the topic. So let's start with representing molecules. There are several ways. The most obvious one is representing molecule as a graph. You have atoms as nodes in a graph and bonds as edges. You can use inkai. It is string-like identifier that is based on the formula, but it lacks information about the structure of a molecule, which is solved by SMILES format. It is another string-like format that encodes information about the structure of a molecule. Based on SMILES, you also have SMARTS format that is regex-like language for specifying substructure within a molecule. And most importantly, you have molecular fingerprints that are sort of automated feature extractors that turn molecule, most commonly in SMILES format, into either count or binary vector. So these all are representation of methanol. So you have inkai, you have SMILES. SMILES data often skip the information about hydrogen atoms. We have SMARTS. So as you can see, this SMARTS tries to match these two groups. I don't remember how are they called in English. You could also have molecular fingerprint, and its shape depends on the type of fingerprinting algorithm used. There are several of them. For the sake of this talk, we will use Morgan fingerprint. And you obviously can use a graph that is just structural formula of given molecule. So, what is this important task of chemoinformatics? Virtual screening. Imagine you are a chemist in a lab and you want to synthesize some molecule with specific set of properties. You probably wouldn't want to sample molecules at random in search of some properties. You would like to reduce the space of possible molecules, which is very vast. It's like 10 to the 60th, I believe. So we would like to get a subset of this set of molecule that would have a high likelihood of having some interesting properties. For example, being active orally or something like that. So to do this, if you have a molecule that have some properties, you can expect that molecules that have similar structure could potentially have similar properties. So you would like to have a way to compute similarity between molecules fast. So if you have a molecule in string-like format, it would be pretty difficult to measure it. So you would like to encode the molecule firstly as in SMILES format, so you would have information about its substructure, and then turn these SMILES into a molecular fingerprint, so a vector. For sake of simplicity of this talk, let's only consider binary vectors. And when you have vectors, you can compare them fairly easily. The most common metrics to do in chemoinformatics are Tanimoto, Dice, Kulczynski, and Rand, and we'll focus on Tanimoto here. You could implement those yourself, but the smarter way would be to use some third-party library to do so. So let's see what chemoinformatics ecosystem has in store for us. The most relevant, I would say, and well-known, most widely used library is RDKit. So it's a toolkit for many chemical tasks written in C++. Hence, it is really powerful, but it has some drawbacks. Main ones, I would say, are the C++ code itself, which made the documentation hard to read for people who are not well grounded in computer science. And thus it's less comprehensive, I would say, and it's not very well suited for Python data science environment. You need to do some wrapping around it to put it in your pipeline. So as a other approach to RDKit, I and my research team are developing scikit fingerprints, which, as name suggests, is interoperable with scikit-learn, so you could easily use it in your existing machine learning pipelines. It comes with many ways to measure similarity, many inbuilt machine learning algorithms like k-nearest neighbors, many fingerprints, as the name suggests, etc. So now I would like to show you how to implement this Tanimoto similarity first in naive way, not optimal, and we'll from there arrive to the scikit fingerprints implementation, which is rivaling the RDKit one in execution time. So, given two vectors, or maybe in this case two sets, A and B, Tanimoto similarity is their intersection divided by their union. And as I said, it could work either for binary or count values, but we'll use binary as example. So the naive way to implement Tanimoto similarity in Python would be to take sum of products of two fingerprints as their intersection, take sum of both fingerprints, and compute their union as sum of sums previously computed minus their intersection, and return intersection divided by union. This is how would you do it for pairwise computation, vector against vector, but you could also do it in bulk with one vector, which represents the query molecular fingerprint that you would like to use as a query for your search, and n-dimensional matrix that represents other fingerprints to be compared. This way you can just do it in bulk, comparing query molecule to each row of the matrix. So, naive way would be to do it like this. You have two fingerprints as an array, take intersection, sum the fingerprints, take the union, return intersection by union. This is how you would do this naive approach in bulk, but there are several issues with this code. So, for starters, it is inefficient in time because you need to do 3 full array scans to get the sums, and it is also inefficient in regard to memory because you need to store the product of fingerprints in separate array. What we can do about it? We can change full array scans for dot products from NumPy, which utilize basic linear algebra subprograms, thus being faster than summation. So intersection in this case would become dot product of given vector A and vector B would become intersection would become dot product of vector B and vector A, and union would be equal to that product of A with itself plus that product with B with itself minus the intersection, so that product of A and B. And we can also reduce the space requirement by changing the type to booleans, since we are working with binary data. This is how you do it for pairwise comparison. This is how you will do it for in bulk vector versus matrix comparison. There are two optimizations you can come up here to speed this up, which I've implemented for the library. So the first one is possibility to skip the dot products, since NumPy's implementation of dot products treats arrays as numerical values no matter what type you use. So instead of dot products, we may use bitwise operation, which with specific CPU instructions will be faster than the dot products. So intersection would be logical end of on bits inside a vector, and union would be logical OR of said bits. And the last optimization you can do here is to use numbajit. And for those of you who don't know what numbajit is what numba is. It's a just-in-time compiler for Python built using LLVM. It just compiles Python, and it puts some constraints on your code, because you have to, for example, define your types, which Python developers don't like to do very much. But in exchange, it gives you possibility to write compiled code. But what is more important in this context, it allows you to parallelize for loops, which will come in handy while doing bulk operations. So this is pairwise approach without number, because if you don't use for loops, there is not much benefit from number in this case, but the binary operators give us some speed up here. This is first variant of how you can do it with number. We have the X matrix passed as an argument to this function, and we compute similarities between each row in this matrix, each one being a vectorized molecule. Thus, resulting matrix would be symmetric. You can see this numbajit decorator here. This means that number would run in no Python mode, so it would try to avoid Python interpreter altogether. In second approach, you can use two matrices instead of one, X and Y, and you would compare rows of said matrices. So how does it turn out? For pure NumPy, there's no difference between pairwise and bulk methods. It's like a couple hundred of milliseconds, but in this order of magnitude, it's not much. For bitops, it's better, but where this logic shines is when we use number. You can see that pairwise calculations are not that good compared to RDKit, but where it comes to bulk, it is almost 2 times faster than code written in C++. Keep in mind that we are using Python here. So if you squeeze all the possible performance out of Python, it can, in this case, run faster than C++, but you have to keep in mind that RDKit does not use this many-to-many approach that we use with two matrices that I showed you. So if RDKit developers ever come up with this optimization, their C++ code will be most likely faster than my Python code. But for now, if you would like to measure some chemical distances, my code could be a way to go for it. So if you would like to see what my team is currently working on, the left code is for you. If you would like to keep in touch with me, the right code is the way to go. Thank you.
Thank you very much, Adam. We have time for a few questions. Maybe I start with the question, how big are the molecules which you are considering in your tests?
From 50 to 100 atoms, I think.
Okay. And the complexity, how complex are they typically? Is
I mean,
more linear?
Most of them are organic compounds, so I would say they are pretty complex by nature.
Yeah.
They are not as complex as something like proteins, but I would say this is not the easiest target. It's not like you are trying to predict properties of some trivial compound like methanol that I showed you, but it's not the biggest molecules you can get. Somewhere in the medium size range, I would say. We have question in the back.
A follow-up question too. So I'm a biochemist, and so I'm interested when you do this modeling to guess which molecule is, I don't know, the best. What do you consider other than structure? Because you probably take some data about existing drugs and look at their fingerprints, right? So what do you put into the models that predict which potential new molecule is the best?
Okay, so
what information
it obviously depends on the task you are trying to do, but from my research, what I could say that besides the structure, you have also the Boolean flag, whether indicating whether something is, for example, bioactive orally. Yes, so basically, what this boils down to is just structure, I would say. But you could encode more than just structure. You can also do isomers, I would say. You could, yes, but in this talk I was considering something called canonical smiles that does not account for isomorphism of molecules, but you could also use isomorphic smiles that does, but I haven't done it myself.
Further questions? Doesn't seem to be the case. Then thank you again once more.
So USB-C. Yes. Is this the adapter or that one's better?
This one's already working, so let's not change it.
Yes. Sounds good. Perfect. Use allow. Yes, start mirroring. Don't set up keyboard.
Okay, and now the magic button, and it works.
Okay. Okay, let's see.
You can use this mic or this one. Actually, this one maybe we can bring back here to get the questions from the audience.
I can try the lapel. If that works, that would be good.
I think this microphone was always much more stable.
This one?
Occasionally
It
there
also
have
kind
been
of
some
depends on
issues.
where you clip it. If you like do it here, it should be fine. If you do it like on the lanyard moves and it gets unstable. So if you
can try,
like
and
here, or
if it doesn't work out, you can always switch.
yeah.
You can always just go here. It's like, do this button. And we can do it here. This one. That way. It should really move.
No, somewhere here. Yes.
Oh, yeah. I think I'm good. I'm on. Alright, so we just now we wait.
So this is 15 plus 5. So I'll give you a sign already after 10 minutes.
Okay.
Then we still have 1/3 of your talk. So the 5-minute warning is not to worry about that. And there is some flexibility. I mean, if you talk a little bit longer, then there will be a shorter question session.
Yeah.
No problem.
That makes sense. Because I think the next event starts.
I mean,
4:30.
there's no problem at all.
Okay. Sounds good. Thank you very much.
Open the door that maybe some more people come.
Yeah, of course. I might actually. I'll go get a.
Using that one by default, and I can maybe take just one for questions.
Yep, sounds good to me.
In case you have some problems, you will just...
Sounds good to me.
Okay, let's come to the last talk of this session given by Igor Tatarnikov. He's with the University College of London.
Yeah.
And we are going from molecules with a certain complexity to something really complex, which is the brain, and we're looking forward to your talk.
Yes. Thank you very much. I think it's doing the buzzing thing. Hi everyone, thanks for sticking around for the last talk of the day. Like I was introduced, my name is Igor and I work as a research software engineer at the Sainsbury Wellcome Center at UCL, where part of my job is maintaining a suite of packages called BrainGlobe, which specifically focus on doing analysis in atlas space or kind of in a common coordinate framework. If you'd like to follow along with the slides, that's the QR code for the slides itself. But I'm going to go through a brief introduction to what an atlas is. Then I'll go through counting cells in atlas space, segmentation in atlas space, and then lastly, visualization in atlas space. So a brief introduction to atlases. What is an atlas? So at the core of everything, an atlas is a combination of some sort of template or some sort of reference image, and this should potentially, hopefully, be an unbiased population average of what you're trying to study. And this is combined with some sort of annotation that is based on either anatomical features, biochemical features, functional features, whatever it might be, but some sort of mapping onto the template. And together, these kind of define a common coordinate framework. So this is a space that I can talk to other researchers, and other researchers can talk to me and say, I did this experiment here, and these are the results I got. Why is it useful? Like I was saying, it is a standardized annotation and coordinate system, so it allows research to be shared in a more fair and accessible manner. It is a target for registering experimental data, so you can use image registration to register your data onto the Atlas template, and that kind of gives you a whole bunch of things for free. So you can then transform your annotations onto your data, or go the other way and transform your data to the Atlas space itself. And lastly, it gives you a simpler way to compare across multiple subjects. So each brain or each organ can be slightly different, and so doing this registration allows you to visualize samples from multiple subjects in one common space, whereas that's kind of hard to do if you don't have this common space. How do we get this unbiased population average? So atlases don't necessarily have to have a population average as the reference image. They can be just single subject. However, if you want an unbiased population average, you would want something that has both an average intensity and an average shape for the population that you're studying. And we do this through an iterative process using ANTS, its registration toolkit. And you would then first initially pick one of your samples as a target, register everything to it, transform all of your images to it, and then average those images. So that gives you the mean intensity of the samples that you're trying to study. You would then take the transforms themselves, average them, and invert them to get kind of an average shift you had to do to get all of these brains into the same area. And then you would then apply that transform to the mean image to kind of get it into a space that's not exactly like any brain itself, but it kind of sits in a middle space that's kind of like all brains, but not quite any specific brain itself. And that makes it an easier target for registration, because if you pick a subject that is a huge outlier, it's a bigger distance for registration to go. And so you kind of want it to be sitting somewhere in the middle of shape and intensity. And these are kind of some of the results. So this is only 8 subjects. So you can take the row at the top is just a single subject. This is a brain scanned on a serial section 2 photon microscope. But at the top, it's a single subject. It's quite noisy. There's some sort of injection site on the left. However, when you take these and average them with just 8 subjects, you get this really crisp resolution. And this is much easier to annotate. And this is kind of a zoomed in area. So it's much easier to annotate. Anatomical features pop. So typically you would assume averaging results in blurring. But here, because we're also registering the samples together, averaging kind of actually results in sharpening of the features in and around the image. So what Adam Tyson, the person I work with, identified is that all of these atlases were being built. However, they were kind of model specific. They were specific to imaging modalities, anatomical focus, developmental stage, and they were kind of all spread throughout. So there was no common way of accessing these atlases, even if they do exist and they've been created, published, painstaking work. And so what we created is the Brain Globe Atlas API, and this is a way of packaging atlases in such a way that they're accessible to tools in a common format. And so we have atlases from many species, many developmental stages, and we're expanding across from the brain into other organs as well. And what this looks like is that with kind of code that looks like this, you can switch from, you can import any atlas, you can have the template image, the reference image that I was referring to before, you can have the annotations themselves, and you can also query for specific brain areas. So you can say, oh, what is this brain area? Give the mesh, give the full name of it, etc., etc. And you can also get the full parentage of that. So going from the root, which subregions does it lie in? So that's great, but what can you do with it? So this is some of our example data. And so this is a brain scanned on a same thing, serial section 2 photon microscope, and it's about 5,000 pixels, or 5,000 by 5,000 by 3,000. So quite a large data set. It's typically stored as unsigned int16. They're typically about 90 gigabytes per channel itself. And this is kind of what the interior looks like. And a very common question is typically just, I labeled a thing, where is that thing? And so the tool we have for registering these images first takes your sample data and the atlas, applies similar filters to them to highlight certain specific anatomical features or salient features for registration purposes, and then does the registration and in both directions. So you get a transform from atlas into sample space, but also from sample into atlas space. And for visualization purposes, we use Napari. It's fantastic. Very easy to stick visualization on the end of your pipeline, but you kind of get something like this, where this is annotations transformed into sample space. And so now, for free, in a way, I paid compute, but for free, I get my brain completely annotated by typically what would be an expert in a way. And so with this, we can start answering questions about, here are some things, where are those things? And so counting cells in atlas space, I'll go through this briefly, but this talk isn't about CellFinder itself. So in order to count cells in atlas space, we focused on creating a tool that can easily ingest large images. To get around this, we first do a very simple pass through with kind of a filter. We just say, are there enough bright pixels that have the size of a shape in this space? And we mark that as a candidate. So we get a ton of false positives, which is kind of what we want. So we first identified just about any bright circular thing. Because the next step, what we want to do is the actual discrimination step. So we then take these small, we take a small region around that candidate. We extract maybe 50 pixels by 50 pixels by 20 pixels, so it's much more manageable. And we feed that into a machine learning network that then classifies whether this is a cell or not a cell. So feeding this entire image, 90 gigabytes, into a machine learning, like you couldn't do it, but 50 by 50 by 20 pixels, much more manageable, and you kind of get results like this, where the machine learning network itself classifies cell, not cell, and it typically does a pretty good job of excluding things that are on the edges, random bright spots, etc. And this is kind of an iterative human-in-the-loop approach. You can then fix these annotations and go on to retrain the network and relabel again. However, now if you combine that with the registration, you very quickly get to this stage of things, where now you can label and find out exactly which regions your cells were in, how many cells were in that region, without having to painstakingly learn what your region specifically looks like and outlining that region on your samples, on each of your samples. So this is a combination from, I believe, 3 data sets pulled into one space. And then we also spit out kind of a CSV like this, where you just get your cell count and the brain region where it was in. For segmentation in atlas space, we have a tool called brain lobe segmentation, which typically does a very similar trick, where now you can outline and find things in your sample and then transform them into this atlas space, giving you the ability to plot multiple experiments or multiple samples onto one, and also get very quick confirmation, did this thing go where I wanted it to go? Typically, these are surgically implanted, and it's key to know that you actually hit the specific region that you were aiming for. And we can do this with any sort of bulk injection, but this enables you to very quickly find out whether you're in the right area or whether you're in the wrong area, and most importantly, kind of make pretty pictures like this, where you can just overlay things onto one. For all of our atlases, we also package meshes with them, so each brain region will have a mesh associated with it for kind of making visualizations like this. And that brings me on to visualization atlas space, and this is the part that I think I enjoy the most, just because pretty pictures are very nice. And so we have a tool called Brain Render. So this uses Vito on the back end to render the meshes that I talked about before, but you can also put any data that you have transformed or that you have in data space or in atlas space. So once it's in atlas space, you can feed it into Brain Render, and it's going to be rendered on top of any meshes you request, any sort of root structures that you request. And so you can see here we're highlighting the multiple species that we have, and each of them has a brain region that was selected, and this is the same brain region across multiple species. So it allows you to do very quick evolutionary comparisons to see how did this brain region change, how did the locality change, etc. But you can also use this in combination with data that you got, say, from CellFinder. So here, the pink cells were detected by and counted by CellFinder, transformed into atlas space by the registration tool itself. But like I said in the past, working in a common coordinate framework also allows us to use publicly accessible data that also exists in the space. So the blue outlines you see is data collected by the Allen Institute and made publicly available. And because we are working in the same space, we can actually overlay this onto our data and kind of get extra context outside of even the brain regions or anything like that. I think I sped through that very quickly, but I would like to thank everyone for sticking around. I know it's the end of the conference and it's been a while. And I'd like to do some acknowledgements. So most of all, Adam, he started the BrainGlow project. Alessandro, he is the co-technical lead on the project right now. And Nico does a lot of the atlas building himself. He came from the MRI space, so he has very deep knowledge of human atlases and how they're designed. And most of all, our funders that allow us to work on software projects, not for fun, for a purpose.
Thank you very much for this interesting talk.
Yeah, thank you. Very awesome work, especially these last visualizations. They were really cool. So I have a specific question about the plotting of the probes.
Mm-hmm.
So I think in your example, you said you would have the brain scan of each animal where you implanted the probe, and then you register the brain scan, and then you plot the probe after registering the brain scan to the template. Is that correct?
Yes. Typically, the workflow we suggest is to transform the data into atlas space and then do the outlining on there. So with probes, we treat them as one-dimensional objects where you add points along the line, and then they're interpolated across as the probe.
Right. So if I would only have probe locations, like I think I'm working with some of the with one data set from the Allen Institute.
Mm-hmm.
I don't think they include the brain scans. If they did them, I don't know. But you get like the neuropixel probes or whatever, and then you get like the coordinates of the probes in the Allen coordinate frame. Would it work the same? Like if you can't do so you can't just also register the probe directly without having the brain scan? Would you be like less accurate than if you would actually be able to register the brain scan as well?
So if it's Allen, I think they're already existing in Allen space, so you could just take those CSVs, those coordinates. I think they are in this space, so you could just plot them all over each other and highlight your regions of interest, whatever it might be. Typically, I think they provide everything in the CCFv3, the Common Coordinate Framework version 3. So you should be able to just plot them in and render them.
I'll try it out once I get home.
Yeah, for sure.
Hi, yeah, great talk. I was just wondering if you, the input data you use is always like a 3D scan of the whole brain, right?
Yes.
Would something like a in vitro brain slice, which you have, I don't know, cancer cells, for example, detected in there, would that be able to be mapped as well, into the brain, or into the bigger model, so to speak, and the segmentation?
Yes, with caveats. So we're working on this right now. Initially, we're using elastics. So the BrainReg uses NiftyReg. It's an MRI-based medical registration framework. We're working on using elastics to do just that. So either 2D plane registration into a whole 3D volume or a 3D subvolume into the entire 3D volume. At this point, it's manual in terms of the initial alignment. So you pick the target that you want to register to, and then you can go ahead. We're working on creating something that can get you close. So something that kind of optimizes your position with a basic affine transform, so not really doing the entire registration process, estimates your location and says, is this good? And then goes through with the next thing. So yes, it's coming soon.
All right, thank you.
You're welcome.
Further questions?
I think there's a question in the back.
I wanted to ask, is there some sort of a limit as to like the resolution that is available? Like whatever you submit, it can, and train it to do that, it can detect that. For example, not just finding cells, but perhaps looking into patterns of like protein localization. Like how does that change? Is it possible to do that too? For example, in cells.
Yes. Currently, one caveat, CellFinder specifically does need 3D because it doesn't work in 3D. We're working on something that would work in 2D, but you would have to hack it a little bit in the sense that you would shrink your cell diameter to be the expected size of your point, given that you provide the pixel-voxel resolution, but you would have to hack some sort of maximum to say that the object should be no bigger than this space itself, because depending on the staining, it might have larger chunks, but you could, and somebody has tried to, and I think semi-successfully used it to detect dendritic outgrowths in a 3D brain. So it is possible. Yeah.
There's a chance to ask.
I think there's one more.
Question.
You mentioned a segmentation tool.
Yes.
Maybe I missed that, but what did you exactly use for this 3D segmentation?
So,
or is it side by
for 3D segmentation, we actually rely on Napari's fancy 3D paintbrush. So you can segment in 3D and kind of paint the object in 3D. However, we also support, you can segment in any program of your choice, as long as it's imported into Napari as a labels layer. It can then be used and transformed into Atlas space if you have registration itself. And that's for the 3D segmentation. The 1D segmentation, I think, is just points. So you click and drop points in Napari, and then they're interpolated as a line by us.
Don't see any further questions, or somebody still want to ask a question? There's no coffee break anymore. People could discuss with you.
Yes, for sure. I'll be around tomorrow for the sprints. You can probably find me in the Napari section.
Okay, so that's actually a good point. Don't forget the next session about the sprint orientation, and there might be some lightning talks, I'm not sure.
It's in the other room, right?
It's in the other room. So let's thank Igor once more for his.
As well. Thank you very much.
Lively discussions, or
yes,
even if it's the last one, because many people are very interested.
Yes, for sure. Thank you very much.
Very cool, yeah. I just saw in your GitHub organization that Nicholas, the Grosso, is also like a member.
Yeah, yeah.
He's my boss, basically. Like,
okay, yeah.
Well, but he's not. Is he currently like involved with the project?
No, I don't think so.
Okay.
So there's quite a few
older
members.
Yeah. Okay. I have to ask him what his like involvement with the project.
Yeah. So I only joined.